We're continuing our discussion on the analysis of one quantitative variable, but specifically today we're going to start discussing statistical inference and how to make statistical inferences for that type of data. As a reminder, a statistical inference uses information from a sample to make an inference or a conclusion about a population. Ultimately, when we make that statistical inference, we'll have to use specific information from the sample, which usually takes the form of a statistic. And when we're talking about one quantitative variable, our statistic that we will be using is going to be xbar. So we are going to use xbar as our statistic to make an inference on a population value or a parameter. So if we're still discussing the type of data one quantitative variable, we have the statistic, meaning the information from our sample, is xbar, and then the parameter that we will try to make an inference on using xbar is going to be mu. So we're specifically talking about using a sample value or the statistic xbar to try to make an inference or a conclusion about a population value or the parameter mu. Now, one thing to remember about parameter values is that they're not moving targets. So a parameter is going to be a measurement that is fixed and unchanging. So when I use a different sample or I take a different sample, I'm still trying to estimate that same parameter. So we expect that it's not a moving target and those measurements are fixed and unchanging. So remember, when you take a sample, you would like to be able to do that randomly, so indicating that you're going to randomly draw perhaps out of a hat. And remember that random doesn't mean odd or weird, it just means that all people have the same chance of being selected. So think about the idea of a population, and again, we are going to try to estimate the value of mu, so the population mean. So I want you to think about the idea of a population where we're going to be trying to estimate the value of mu, the population mean, and then think about randomly drawing out a sample from that population. So if I were to draw out 4 people from a population, the value that I would use to describe that sample is going to be xbar. So maybe I'm looking at average weight. If I had a sample of people and I added up their weights and divided by 4, I would get a value of xbar. Well, if I took another random sample out of the same population, but then I found 4 different people, I would still have a value of xbar, but I would have a different value for xbar. So I would have a new value for xbar. So if I took a new sample of people, I would have a new value of xbar. It's still xbar because it's still from a sample, but it's a different value of xbar because I have a new random sample. And I could continue doing that over and over again, and if I were randomly drawing people out of the population, I would have a new or different value of xbar each time. So what would happen then is you would end up having a list of all possible values of xbar, which essentially would create a whole new population. So instead of a population of people, it's kind of weird, it would be a population of values of xbar. Now, the point of this, and why would you create a whole population of values of xbar, is to understand the characteristics of xbar. So to be able to understand how to use xbar to actually estimate or make a statistical inference on mu. So the characteristics that we need to understand to be able to use xbar is first going to be the mean of the sampling distribution of xbar. Then we would also want to know the standard deviation of all possible values of xbar, and finally the shape of all possible values of xbar. If we knew all of those things, we could describe the characteristics or the population of all possible values of xbar, and that description is actually called the sampling distribution of xbar. So if we wanted to look at an example, we could look at the example that's shown in the textbook, where it's based on the American Community Survey, looking at the average number of children born to American women in their or her lifetime. So we know that from the population, the average number of children born to an American woman in her lifetime is 1.9. So that means that mu is equal to 1.9. So we know that the value that we're trying to estimate is 1.9. Now here are 4 different situations or different samples that we have taken. Samples where the x-bar is made up of an n equal to 2, and then situations where the samples or x-bar values are made up of n's equal to 5. And this is going to be a situation where the x-bar values are made up of samples of size 20. And finally, where x-bar values are made up of samples of size 50. So remember that these distributions, because we're talking about a sampling distribution, are making up all possible values of x-bar. And so you could visualize that these are stacks of x-bar values, not people. So what you'll notice as you see the sample size increasing, so going from 2 to 5 to 20, and then finally to 50, what you'll notice in terms of the center that we're trying to estimate of 1.9, it actually appears that the center each time is approximately 2. So that indicates that the values of x-bar are centering themselves around mu, which is the value that x-bar is supposed to estimate. So that's a good thing. We know that all of these distributions, despite sample size, are going to try to center themselves around the population mean mu, which is what all of these x-bars are trying to estimate. If you think about the variability of the sampling distribution, you can think about that in terms of how wide this distribution is, and you'll notice that this one ranges from 0 to 6, and then when we move up in sample size, this is from 0 to about 4, and then this one actually seems to range from 1 to about 3, and then it appears that we go down to maybe 1.5 to 2.5. So what appears to happen to variability as we increase in sample size is that it decreases. So it appears that the variability decreases as sample size increases. And then finally, in terms of shape, when you increase in the sample size, it appears that the graphs or the distributions begin to look more and more bell-shaped. So what we know then from the sampling distribution of the sample mean is that all of the x-bar values will center themselves around the population mean. We also know that variability, which is a measurement of standard deviation, or variability is measured by standard deviation, is going to use the formula sigma, which is population standard deviation, divided by the square root of n. So because n is in the denominator, we can see that as it increases, variability will decrease. And then finally, we know that for the shape, as we increase in the sample size, it will begin to look more and more bell-shaped. So there's this theorem that's represented called the central limit theorem when you're talking about one quantitative variable. And you may wonder then, how big does the sample size have to be for you to be able to get to that bell-shaped distribution? Well, truthfully, it's hard to approximate what sample size is necessary or large enough for you to get to that normal curve. And the best answer is it depends. So it depends on the number of outliers. It depends on the original population. So that's not an easy question to answer right away. But these are the things that we know about the sampling distribution of x-bar.